the chemact 3 and this corresponding video, we will explore the properties of atoms, ions, and isotopes from the perspective of the constituent subatomic particles. Let us begin with a bit of atomic humor. Here is a cartoon representing two atoms, although I did not know that atoms had arms and legs and can talk, for that matter. These atoms are involved in some kind of military combat. One atom claims to have been hit and has lost an electron. When asked if they're sure about this, they say they're positive. Of course, the humor in this cartoon comes from the double meaning for the word positive. Yes, the atom is certain that she has been hit, and if the atom has lost an electron, then she would be positively charged. Clearly, this cartoon would be meaningless to someone who has not studied chemistry. But hopefully you recall that atoms consist of protons, neutrons, and electrons, and that the number and balance of these subatomic particles will determine the elemental identity and atomic properties such as mass and charge. The intended learning outcomes for this video and chem activity are that you would be able to state the properties of protons, electrons, and neutrons in terms of their relative mass, relative charge, and position in the atom. That you would be able to define the terms mass number, atomic number, and isotope, and explain how isotopes of an element differ. That you would be able to state the symbol for an isotope given its mass number and atomic number. And finally, that you'd be able to calculate the number of protons, electrons, and neutrons in atoms and ions from the mass number, atomic number, and charge. Ultimately, we will explore and unpack details in this diagram from Teaching Model 1. But first, I would like to explore some online simulations. The web addresses for these simulations are shown in the course pack in chemact 3, and therefore you are encouraged to explore. The first simulation is called Build an Atom. Of course, none of the representations are to scale, nor is it realistic to be able to add and subtract atomic particles at will, but the simulation does allow us to easily see how the type and number of subatomic particles determines the atomic properties. Adding one proton produces the hydrogen ion. This tells us that the number of protons is connected to the atom identity, and that a proton has a +1 charge. A positively charged particle is called a cation. A single proton contributes a single unit to the mass number. A single neutron also contributes a single unit to the mass number, but has no influence on the atom identity or charge. Both of these particles reside at the core of the atom, known as the nucleus. A single electron makes no contribution to the mass number, contributes a single negative charge, and has no influence on the atom identity. Also note that the electron resides in some region outside the nucleus. If we now add a single proton and electron, the positive and negative charges balance, and we generate the hydrogen atom versus the hydrogen ion. Clearly, the magnitude of the charges for the proton and the electron are the same, but they're opposite in sign. As expected, the mass number is 1 due to the single proton present. If we add an additional electron, the number of electrons exceed the protons, and as expected, we have a negatively charged particle. This is called an anion. Returning back to the neutral hydrogen atom, if we now add another neutron, we see the mass number increases to 2, but we still have the hydrogen atom. This introduces us to the concept of isotopes, atoms of the same element that differ in the number of neutrons. This example also makes clear that the mass number is the sum of the number of protons and neutrons. Adding an additional proton changes the identity of the atom from hydrogen to helium. Clearly, the identity of the atom is associated with the number of protons. Because the number of protons exceeds the number of electrons, the particle is positively charged. Adding an electron generates neutral helium. While there are many more combinations that could be explored, let us turn our attention to another aspect of the simulation. Here we will see how chemists usually represent the subatomic particles when communicating with other chemists or scientists. Rather than sketch an atomic model, chemists typically use symbols to represent the number of subatomic particles present. Let us quickly go through the changes we saw in the first part of the simulation to see how these affect how the symbol is represented. When we add one proton, we see the symbol H for the hydrogen cation, an orange 1 for the number of protons, and a black 1 for the mass number. Add an electron, and the charge is neutralized. Add another electron, and the symbol indicates a hydrogen anion. Finally, we return to a neutral hydrogen atom and add a neutron, and the mass number increases to 2. The symbol indicates a different isotope of hydrogen. Finally, we add another proton and electron, and the symbol changes or indicates a neutral isotope of helium with a mass number 3. Let us now return to the diagram that is found in your course pack under Teaching Model 1. Many of the concepts we explored in the simulations are summarized here. All the boxes in the first row represent different forms of hydrogen. These all have a single proton in the nucleus, and the number in the bottom left-hand corner is the same in all cases. This is highlighted with a green oval. This number is called the atomic number and is abbreviated by the symbol Z. It indicates the number of protons. It also indicates the number of electrons for a neutral atom. Note that the term neutral atom is actually redundant in that by definition an atom is neutral, but we add the word neutral for emphasis. Equally important, the atomic number reveals the atom's identity. Atomic number 1 is hydrogen. Atomic number 2 is helium. Atomic number 6 is carbon, and so on. The left-hand box, first row, represents a positively charged ion called a cation. This occurs when the protons exceed the electrons. And of course, this can only happen when one or more electrons are lost. On the right-hand side, for both rows, we see examples of anions. Again, this can only occur when electrons exceed the number of protons through a gain of one or more electrons. The two middle boxes in the first row give an example of two atoms of the same element that differ in the number of neutrons. Their mass numbers, which is the sum of protons and neutrons, is different. These are clearly examples of isotopes. We need to discuss one other aspect of this diagram. Notice that each atom or ion is associated with a specific mass. For instance, this cation has a mass of 1.0073 atomic mass units. The symbol used is to represent this unit. An atomic mass unit is defined as one atomic mass unit is equal to 1.6606 times 10 to the minus 24 grams. Because atoms and ions are so tiny, it is impractical to refer to the mass in grams. So we use atomic mass units instead. It is crucial that we make the distinction that the mass of an atom or ion in atomic mass units refers to a different concept than the mass number. The mass number is the sum of the number of protons and neutrons. In other words, the number of particles located in the nucleus. Whereas the mass is the result of a physical measurement using an instrument called a mass spectrometer. We will discuss this instrument in the next activity. It is interesting to compare the mass of a hydrogen cation to the mass of the hydrogen atom. The difference in the masses is of course related to the tiny mass associated with the electron. Finally, you may be wondering why the mass of neutral carbon-12 isotope is exactly 12 atomic mass units, whereas the masses of all the other atoms and ions are expressed as non-integers. Again, this is connected to how the mass of an atom is determined by a mass spectrometer. We will discuss this in more detail, but for now, suffice it to say that carbon-12 isotope is used as a standard against which all other atoms and ions are compared. Its mass is arbitrarily set to be exactly 12 atomic mass units.